So from our derived circuit, we wire it up. We find out the first instant name G1 is a 2-input AND gate that we have included a while ago as a component N to B1. And the connection there is the formal output is to be associated to the user signal S1, and the first inverted input I0 is to be associated to the inverted input, which is Qin in our case. And then the next input I1 is to be associated to the J input of the JK flip-flop that we're designing. So this is basically the structural description of creating JK out of data flip-flop. Of course, here it's not clear because we don't have the schematic here, but we derive this in the class. And the gate 2 is the instant name of the N2B1 also. And then G3 is the 2-input NAND gate, both inputs are inverted, meaning to say this is basically a 2-input OR gate. And then we have the G6 being the inverter. Then we follow it up with the data flip-flop with an instant name of DSS. So the output is associated to variable Q internal. The clock is associated to the generated debounce button. So we're using the debounce button, which is obtained by, after waiting 40 milliseconds, we use that signal to clock this data flip-flop. And the clear formal is connected to the external reset, and the D is to the user variable data that we provide in the port entity. Then we transfer the internal Q in to the output Q. Now,
Tony's tire ready?
To debounce the input B button, so here is a process to do that is sensitive to the system 50 megahertz clock reset and count. So if any one of these three changes, this group of enclosed in the begin end will be triggered to execute. So the highest priority to be examined is whether the reset is active high. If it is, then initialize the count to integer 0, as well as initialize the 100 hertz clock. If it is not reset high, that is the meaning of else if, then we check whether the count is 500,000. If it is, then we initialize the count. Otherwise, if it is not 500,000, then we check whether the system 50 megahertz changes is positive age. That is the meaning of this line. If it is, then we initialize the count and increment the 100, complement the 100 hertz clock, so it will create a 100 clock, which is 100 hertz. And that's the end of the if, and then you increment the count. But to make this to serve as your assignment, I blotted out here the necessary step requirement to produce a 40 millisecond delay clean debounce button that will be used to clock the data flip-flop, the one that just we read off a while ago. So it is created by using a process sensitive to the input bouncy button B and the clean debounce 100 Hertz as well as the reset. So out of this, it will create a BD, debounce button, which is part of this assignment you have here. So basically, that is the end of our VHDL code. But a small observation shows this data conversion, one input data line to be converted to input JK, meaning to say overall the input is JK, and we use the 1-bit input data to create that overall. It has a slight flaw though. You will find out if the input JK is high and anything for K, pressing the reset button does not reset the Q output line though, that is connected to LED 0. While all the other characteristics of a typical JK works quite correctly. And I was proposing here maybe you can fix the problem. If you can, then this is qualified to serve as one of the possible 4 assignments that you're required to do. So that's all it is. And in order to clearly understand this multimedia, you got to review the schematic that we have derived so you can correctly verify the structural VHDL description that we just laid out. Okay, I will publish now.